All right, let's dive into a real classic today. We're tackling problem 1.126 from Irodov's legendary physics collection. It's all about power and circular motion. And if you've ever found these problems just a little bit tricky, trust me, you are in the right place. We're going to break this thing down together. So here's the big question, right? The problem gives us information about acceleration, but it's asking for power. How in the world do you get from one to the other? It might seem like a huge leap, but I promise you, there's a super clear, logical path that we're going to walk through, step by step. And here's our roadmap for this journey. First, we'll decode the problem itself. Then, we'll map out our plan of attack. After that, we'll jump into the fun part, calculating the instantaneous and average power. And finally, we'll wrap it all up with a quick recap. Let's get to it. Okay, first things first. Before we even think about writing down an equation, we have to make sure we know exactly what the problem is telling us and what it's asking for. This is, without a doubt, the most important step in solving any physics problem. So, what's in our toolbox? We've got a particle, it has a mass m, it's moving in a circle with a radius r. But here's the key piece of information, the real heart of the problem. Its normal acceleration, Wn, is not constant. It's actually changing over time, following the rule Wn equals at squared, where a is just some constant. And what are our targets? We have two very clear goals. First, find the instantaneous power, P, as a function of time. You know, how much power is being pumped in at any given moment. And second, we need to calculate the mean or the average power, we'll call it P, over the first t seconds of its motion. All right, we know our givens, we know our goals. Now it's time to build our conceptual roadmap. A good strategy is everything here. Now, this slide right here is absolutely crucial. It clears up what is probably the biggest point of confusion in circular motion. You have to understand that there are two totally different kinds of acceleration at play. The normal acceleration, Wn, the one we were given, that's the centripetal one. Its only job is to change the particle's direction, to keep yanking it toward the center so it stays on that circle. The other one, tangential acceleration, Wt, does something completely different. It changes the particle's speed. It's the gas pedal or the brake. And here is the giant aha moment. Think about it. Power is all about doing work. And you only do work when a force pushes something in the direction it's already moving. The normal force, which causes that normal acceleration, is always pointed to the center. It's always perpendicular to the velocity. So it does zero work. And if it does no work, it generates absolutely no power. This is a massive conceptual shortcut. It means we can totally ignore the normal force and focus only on what's happening in the tangential direction. And that insight leads us to this beautiful, simple, four-step chain of logic. This is our game plan. Step 1, we'll use the normal acceleration they gave us, Wn, to figure out the particle's speed, v. Step 2, we'll find how fast that speed is changing, take its derivative, to get the tangential acceleration, Wt. Step 3, we'll use Newton's second law to find the tangential force. And finally, step 4, we'll combine that force and the speed to get the power, P. See? It's a straight shot from what we're given to what we need. All right, the plan is in hand. Let's do this. Time to execute and find that instantaneous power. Okay, step 1, find the speed. We know the fundamental definition of normal acceleration is v squared over r, and the problem tells us it's also equal to at squared. Well, if two things are equal to the same thing, they must be equal to each other, so we just set them equal. A little bit of algebra to solve for v, and bam, we've got our speed as a function of time. V of t equals t times the square root of ar. Step 1, done. Moving on to step 2, finding the tangential acceleration. By definition, this is just the rate of change of speed, dv over dt. We just found v of t, so all we have to do is take its derivative with respect to time. And check this out. The derivative of t times a bunch of constants is just the bunch of constants. So our tangential acceleration w is just the square root of ar. It's a constant. Isn't that interesting? The particle is speeding up, but its rate of speeding up doesn't change. On to step 3. Find the tangential force. This is just good old F equals ma, but specifically for the tangential direction. So Ft is going to be m times Wt. And since we just found out that Wt is a constant, well, that means our tangential force is also constant. It's just m times the square root of ar.
And now, for the grand finale of part 1, power is simply the tangential force times the speed. We have our constant force, F tau, and we have our speed, V of t. We just multiply them together. The two square roots combine beautifully, and we get our first answer. The instantaneous power, P of t, is equal to m/r/t, a nice, simple, linear function of time.
Awesome! We have our first answer. Now, let's tackle the second part of the problem, calculating the average power. So, how do you find the average of something that's constantly changing, like our power function? Well, calculus has our back. The basic idea is you find the total accumulation of that thing over some interval, and then you just divide by the length of the interval. For power, the total accumulation is just the total work done. So we're going to integrate our power function from time 0 up to t, and then divide the whole result by t. So here's what the math looks like. Our average power, P, is 1 over t times the integral of our power function from 0 to t. Now, you'll see we're using the Greek letter tau, or tau, inside the integral. That's just a dummy variable, so we don't get it confused with the t in our limit of integration. All those constants, m, a, and r, they can just be pulled right outside the integral, which leaves us with a super simple integral of just tau. And the integral of tau is just t squared over 2. Evaluating that from 0 to t gives us t squared over 2. We multiply that by the constants out front, do a little cancellation, and boom, there's our final elegant answer. The average power, P, is m/r/t divided by 2. And hey, look at that. That's exactly half of the instantaneous power we found earlier, which makes perfect sense, right? For any function that starts at 0 and grows in a straight line, its average value is always going to be exactly half of its final value. And just like that, we've solved it. Now let's do a quick recap to really lock in these concepts and talk about the common traps to avoid.
So, to put a nice bow on it, here are our two final answers, side by side. The instantaneous power is P of t equals m/r/t, and the average power over that same time is m/p/r/t over 2. Beautifully simple results from what seemed like a tricky problem at first.
Now listen up, because this is really important. These are the traps that people fall into all the time with problems like this. Number 1, by a long shot, is confusing what normal and tangential acceleration actually do. Remember, tangential is for speed, normal is for direction. That leads right to the second pitfall, forgetting that the normal force does 0 work and generates 0 power. It's the key insight. Please don't try to use the total force or total acceleration to find power. It will not work. And of course, the classics. Always double-check your calculus. And I'll leave you with a little brain teaser to chew on. We solved this for a normal acceleration that grew with time squared. What if it was just a constant? How would that change our answers? See if you can take the 4-step plan we developed and apply it to that new scenario. Thanks for joining me.